Welcome back to Future Minds, Gen AI and Data Science. I am your host Manav. I am thrilled to have you with me for our second episode. Today we are going to dive deep into world of neural networks. These powerful models form the backbone of many generative AI systems. Understanding how they work is crucial for anyone interested in AI and data science. So let's get started. First thing first, what is neural network? At its core, neural network is computational model inspired by the biological brain works. It is composed of layer interconnected nodes or neurons which process input data and produce output. This interconnection between these neurons have associated weights that adjust as the network learns from the data. To visualize this, imagine network of neurons organized into layers. First layer, known as input layer, receives the raw data, and this data is then passed through one or more hidden layers where the real magic happens. Each neuron in hidden layer takes input from the previous layer, processes it and passes the result to the next layer. Finally, the last layer called the output layer produces the final prediction and classification. Let's break down let's break this down with simple example. Suppose we are building network to recognize handwritten digits like those from the famous MNIST dataset. Our input layer would consist of 784 neurons, one for each pixel, in a 28 by 28 image. The output layer would be have 10 neurons, one for each possible digit, like 0 to 9. Between these layers, we might have one or more hidden layer with varying number of neurons. During the training process, network learns by adjusting the weights of connection between the neurons. This is done through method called backpropagation, which involve calculating error of the network's predictions and propagating this error backward through network to update the weights. Goal is to minimize the error, allowing the network to make more accurate predictions. Now let's delve deeper into components of neural network. Each neuron in the network performs a mathematical operation called weighted sum, where it multiplies each input by corresponding weight and then adds the bias term. The result of this weighted sum is then passed through activation function, which introduces non-linearity into the model. This non-linearity allows neural networks to learn complex patterns in the data. One common activation function is the sigmoid function, which splashes the input into range between 0 to 1. Another popular choice is the ReLU, rectified linear unit, which output the input indirectly if it is positive or 0 otherwise. ReLU has become default activation function for many neural network because it helps mitigate vanishing gradient problem, which can hinder the training deeper networks. Speaking of deep networks, let's talk about deep learning. Deep learning is a subset of machine learning that involves training neural networks with many layers, known as deep neural networks. These networks can learn to represent data at multiple level of abstraction, making them incredibly powerful for tasks like image and speech recognition. Neural natural language processing, and of course generative AI. One of the most exciting development in neural network deep learning is advent of convolution neural networks or CNN. CNN are particularly well suited for image processing tasks because they leverage the spatial structure of image. Instead of treating each pixel independently, CNN use filters and kernels that slide over image to detect local patterns such as age and textures. This allows CNN to capture hierarchical features from simple edge edges in the early layers to complex object in the deeper layer. For instance, in our handwritten digit recognition example, the early layer of CNN might detect basic shapes like lines and curves, while the deeper layer would recognize entire digit. The hierarchical feature learning is what makes CNN so effective for tasks like detection and facial recognition. Another fascinating type of neural network is recurrent neural network that or RNN. RNN are designed to handle sequential data such as time series or natural language by maintaining hidden state that captures information from previous time steps. This makes them ideal for tasks like language model, machine translation, or speech recognition. However, traditional RNN suffer from the vanishing gradient problem, which makes it difficult for them to learn long term dependencies. To address this issue, researchers develop more advanced architectures like long short term memory LSTM networks and gated recurrent units. These architectures introduce gating mechanisms that allows the network to selectively remember and forget information, enabling them to capture longer term dependencies more effectively. Now, let's tie this back to generative AI. Many state of the art generative models such as GPT-3 are built on the top of type of neural network called transformer. Transformer are have revolutionized neural natural language processing by enabling the training of very large model that can generate coherent contextual relevant text. Transformers use mechanisms called self attention, which allows the model to weight the importance of different words in sentence then making prediction. This enables the model capture long range dependencies and contextual relationship more effectively than traditional RNN. The success of Transformer has led to a wave of innovation in generative AI, from text generative to image synthesis to music composition. As we continue to explore the world of neural networks, we will see how these models are being applied to solve real world problems and drive innovation across industries. In upcoming episode, we will dive into specific applications such as how neural networks are used in healthcare to predict disease outcome, in finance to detect fraudulent transaction, and in entertainment to create realistic virtual character. We will also discuss the tools and framework that makes it easier to build and train neural networks, from TensorFlow and PyTorch to Keras and JAX. These frameworks provide the building blocks of developing cutting edge AI models. We will provide practical tips, resources for getting started with these tools, Whether you are beginner or experienced practitioner, of course, no discussion of neural networks would be complete without addressing challenge of ethical consideration. Neural networks require large amount of data, computational power to train, which can be barrier for many organizations. We will explore techniques for improving efficiency of neural networks, such as transfer learning and model compression. We will also delve into ethical implications deploying neural networks in the real world, from bias in AI models to the potential for misuse. It's crucial to consider the broader impact of this technology. We will discuss the strategies for building fair and transparent AI system, as well as the importance of ongoing research and regulation. As we wrap up this episode, I hope you have better understanding of what neural networks are and why they are powerful. We are only scratched the surface of fascinating topic. There is so much more to explore. Make sure to subscribe Future Minds so you don't miss any our podcast in future. If you have any question, feel free to comment. Thank you for joining me today. Until next time, I am Manav signing off. Stay curious, stay inspired.